In section 8.2, we're going to explain the concept of atomic orbital hybridization, and we're going to determine the hybrid orbitals associated with various molecular geometries. So, valence bond theory works well for linear and diatomic molecules, but it fails to account for the molecular structures we know more complex molecules have. We saw how Vesper's theory was able to recreate the molecular geometries pretty well. But how can we rectify molecular geometry with the bonding based on atomic overlap? So if we look at valence bond theory in the case of water, we get the wrong geometry. We see that these are about 90 degrees apart, and we know that to actually be closer to something like 104. So we introduce hybrid orbitals. And this is where we're going to combine together orbitals of different kinds, S and P's and stuff, to make a hybrid orbital, which is essentially like the mathematical addition of those two areas that the orbitals would occupy. One thing to keep in mind when working with hybrid orbitals is that the number of hybrid orbitals formed always equals the number of atomic orbitals that are combined. So here we can see that Vesper theory would predict that in a water molecule we have a distance of 109.5 degrees to form a tetrahedron. We justified that it was less than that before by saying that the lone pairs are going to occupy more space. But we'll see that with atomic or hybrid orbitals, we actually don't even need that justification. We actually get down to 104.5 degrees, a lot closer with our experimental results. So what are hybrid orbitals? We're going to combine together orbitals of two different kinds. We'll start with just a single S and a single P. The two atomic orbitals can hybridize to produce two hybrid orbitals. These are called two sp hybrid orbitals. This occurs when a central atom is surrounded by two regions of electron density. Unoccupied orbitals cannot hybridize. So let's take a look at what that looks like. So if we have an s orbital and we have a p orbital, their mathematical addition is going to look something like this. We're going to have two hybrid orbitals for the two orbitals that we put in. And when we combine those two together, we wind up getting an orbital that looks like this, 180 degrees apart. If we think about the electronics of that situation, we had two electrons in our s orbitals. In the case of beryllium, after hybridization, one of these electrons is promoted to a p orbital, and we wind up with two sp orbitals and two unhybridized p orbitals at the top. We can have sp2 hybridized orbitals. This is when three atomic orbitals can hybridize to produce three hybrid orbitals of the sp2 type. This occurs when the central atom is surrounded by three regions of electron density. So this time we're going to have two p orbitals. We're going to start with the one that would be end-to-end with the s orbital, and we'll add in one of the other ones. It wouldn't really matter which one. And we're going to wind up with three orbitals that look like this, each aligned down one of the axes. When we combine those together, we wind up with a planar structure with 120 degrees apart. We could also visualize that by essentially looking down this z-axis, and you'll see that drawn commonly when you have crowded structures. Picturing the electronics of this situation, we have three electrons this time, one of them in a p orbital. We wind up with three sp2 orbitals, each singly occupied. Here are some examples of some sp2 hybridized orbitals, or hybridized structures. You're going to see this written a lot in organic chemistry. They'll be talking a bit about the hybridized orbitals. And of note here is on ethylene, the hybridization is actually occurring on both of these carbons. So this guy here is sp2 hybridized, and so is this one here. If you imagine that there is a 1 above the S, then 1 plus 2 is 3. And that will always be the number of things that carbon binds to when you're trying to figure out the hybridization for carbon. So if it was bound to 4 things, it would be sp3 hybridized. If it was bound to 2 things, it would be sp2 hybridized. Or sp hybridized, so on and so forth. sp3 hybridized orbitals is when we have 4. We're using all 3 of our p orbitals now. We get 4 hybrid orbitals, and those are going to combine into that tetrahedral type shape. This time we are using all of our p orbitals, and we wind up with no unhybridized orbitals left over. Here we can picture the formation of ethane here. So we have 1 carbon bound to another carbon, and then 3 hydrogens bound to the periphery of those. We can actually extend this even further when we have metals by including d orbitals. So we can have sp3d hybridization, and that is going to yield us to our trigonal bipyramidal structure. And again, we can even have sp3d2 orbitals with 6 atomic orbitals hybridizing to give us our octahedral structures that we've seen with metals before. If we compare the structures that we got from Vesper theory with our hybridization model, we see good agreement, and we can now describe 3-dimensional geometries.